Poor old tan seems to get forgotten, today we're going to give tan the attention it deserves. All right, so first thing we're going to do is draw the basic tan function. To do that, we'll just complete this table of values. Okay, so let's go to the unit circle and note that when it's 0, it's going to hit the tangent at 0. Pi on 4 is this one here, hits the tangent at 1. Pi on 2 will never hit the tangent, so it's undefined. 3 pi on 2 is down here at -1, 3 pi on 4 rather, and pi, we're back through the tangent at 0. Let's go in the reverse direction now. So we're going to go negative pi on 4 units around the unit circle, so we're going to end up there at -1. That's going to be undefined because it'll run parallel to the tangent. 3 pi on 4 is down here, which will hit the tangent at 1, and negative pi is here, which goes to the tangent at 0. So let's complete this. So it's undefined here, so what that means is we're going to get asymptotic behavior at pi on 2 and negative pi on 2. So there's x is equal to pi on 2, and here is x is equal to negative pi on 2. All right, what else happens? At pi on 4, which is here, we produce 1. At 0, we produce 0. And at negative pi on 4, we produce -1. All right, let's try to draw that part of it. Okay, noting that tan doesn't have that same sort of cubic stationary point of inflection. It sort of cuts through diagonally and then goes back up again. That's okay to do here because it's not a stationary point. It's in fact just an inflection point. Okay, now over to here we've got -3 pi on 4, oh no, +3 pi on 4 and -1. That's that, pi, which is 0. And what that's going to do is basically just repeat this phase. Right, and what should happen is this phase here should go to here. So let's just see if that happens. I'm going to plot the points by symmetry, that there, and let's just check it. Negative pi should be 0, and -3 pi on 4 should be 1. It is. Right, and again, just as accurately as possible, repeat so that it looks like it's exactly the same. Right, so there's our basic tan function. Asymptotes at pi on 2 and negative pi on 2. Asymptotic behavior around those points. All right. So in summary, reminder that tan is equal to sine on cosine, and that's why we get this undefined value is anytime cosine is 0, tan can't calculate. It can't calculate a tangent because you get a divide by 0 error. The graph repeats itself every pi unit, so it's got a different period. Okay, so to separate itself from the seemingly more popular sine and cosine functions, it goes, all right, I'm going to have a different period. Okay, so negative pi on 2 to pi on 2 is a period of pi. So we get repetitions every pi units of time. The range is all real numbers unless it's got a restricted domain. You can calculate the equations of the asymptotes by using this formula here. I don't have a clue what that formula is, and I've never used it in my entire life. I just use transformations. So let's give it a go. All right, pretty nasty looking one here. This is about as hard as it gets. All right, so we got y equals 3 tan 2 x take pi on 8. All right, so I've yanked out the 2. Now we're going to get the period, which for tan is pi, and we're going to divide that by 2. All right, so now what we're going to do is sketch the asymptotes. So I think that might be the first thing that we'll do. And what I'm going to do for the moment is just ignore the translation. Okay, so I'm going to sketch it untranslated and then move each of my points over pi on 8 units. So the asymptotes usually are pi on 2 and negative pi on 2. The period now is half of the original period, which means the asymptotes will have to halve. So it would have an asymptote at pi on 4 and negative pi on 4. Okay, so that is the how do you say, that's the untranslated one. Okay, so we're not doing the translation yet. Right, now for the original graph, or the basic up here, what happened is at pi on 4, it produced 1. So at half the distance from the asymptote to the origin, what we got is a value of 1. Now what's this function going to do? So we're going to half the distance from the asymptote to the origin. That's at pi on 8. It would have been 1, but see this 3 here? That's a dilation factor 3 from the x-axis. So what that's going to do is take that 1 point and put it up to 3. So it's going to be there, and it will be reflected over here. Okay, so that's what's going to happen here is we're going to get tan going like so. Now the only thing is that what we want to do is shift it pi on 8. So everything that I've just done needs to be moved pi on 8 over. So again, what I do is I now switch pen color, and I'm going to move each of these points pi on 8 over. Okay, so that's going to move to there, that's going to move to there, that's going to move to there. Asymptote is going to move to there at x is equal to 3 pi on 8. All right, now the original or the next asymptote would have been, so we've got 2, 4, 2, 4. Next asymptote is going to be there at x is equal to 7 pi on 8. All right, now what we can do is sketch a portion of this. So it would have looked like that. So I'm only going to sketch the portion over the domain required. So that's going to be like that. Okay, so this is going to be a -3, that's going to be a 0, and that's going to be a 3. Again, I'm going to try and draw that like so. It's a little bit wobbly. That looks okay. Right, so there we go. That's that graph sketch done. So key features, when x is 0, y is -3, pi on 8, 0. Don't need that. Labeled asymptote, don't need that point, don't need that point, although it does need to be evident that it's going through like 3 pi on 4, 3. We don't need to label it. 5 pi on 8, 0. Asymptote labeled. All good. Right, so there's our graph sketch of tan. All right, good solve question here as well. Okay, so what we want to do is solve this equation. Okay, well, how are we going to do it? How am I going to work out when cosine 2 theta is equal to cosine, sine 2 theta is equal to cosine 2 theta? Well, I'm going to do a little bit of manipulation on this. I'm going to divide both sides by cosine 2 theta. And what that's going to do is say that 1 equals cosine 2 theta. Oh, no, not that. 1 equals sine 2 theta over cosine 2 theta. Now, what do I know about sine on cos? I know that that's tan. So I'm going to replace that with tan 2 theta equals 1. All right, and this is basically asking the question, when is tan going to equal 1? And we've got a domain of 0 to 2 pi, and we're going to note that we've got a dilation factor of 2. So I've got to double the amount of solutions. So it's first going to equal 1 at pi on 4. Okay, so that's going to hit the tangent at 1 there, and down here at 5 pi on 4. Okay, that's the second time it's going to hit the tangent at 1. So let's list those. Pi on 4, 5 pi on 4. But again, we've got a dilation factor here, which is going to double the amount of solutions that we need to generate. So I'm going to go here, which is 8 pi on 4. This is going to be 9 pi on 4, followed by, what's that? That is like 13 pi on 4. Okay, so now I'm going to divide all of these by 2. So theta is equal to pi on 8, 5 pi on 8, 9 pi on 8, and 13 pi on 8. Right, so that's when this will occur. Let's just check it out on the calculator. So we're going to go ahead and solve sine 2x equals cosine 2x for x, and we feed it a domain restriction because otherwise it'll produce a general solution because there's an infinite number of solutions between 0 less than x less than 2 pi. All good. Okay, so there's a bunch of questions on tan. So get stuck into it. It's a pretty cool function, even though we don't use it much.